Okay. Yes, good afternoon, everyone. Today we're very happy to have Professor Rick van der Ploeg from Oxford University. Rick is a world-renowned economist on natural resources and environmental economics. And now Rick is in Forlì in Italy. I'm very grateful to Rick that he's willing to give us a talk in his early morning. And despite the time difference between us, it's nice that we can all enjoy the best season of the same Mediterranean climate. Spring, yeah. Now in spring in Forlì and autumn in Perth. Today's Rick's topic is about the asset diversification versus climate action. I think it is a very innovative idea to link the asset pricing to environment policy. I just have a quick just read of the paper. I think the idea is just based on the trade-offs between the risk diversification and the pollution abatement. Let's enjoy this talk. And now screen is yours, Rick.
Thank you very much for this kind introduction. Of course, I would have much preferred to be there because it looks so lovely. But who knows, at a future occasion. So I'm going to talk about climate policy. I'm trying to kind of see if I can move my screen. There we go. And this is my outline. I will first do a bit of a review of climate economics as it's been done by people like Nordhaus, but then I'm going to allow for stochastics and use the theory of asset pricing. Then I will look at diversification in asset prices, diversification versus climate policy. And we look at these things. And if we have time, we can look at transition risks. So most of the models that have been used, including the ones by William Nordhaus, who got his Nobel Prize for that a few years ago, are really deterministic. Sometimes they do Monte Carlo simulations, but really they are deterministic. So then recently, some models have been developed that are analytical. And I'm thinking particularly on an econometric article by Golosov and co-authors in 2014. But they are so simple that stochastics don't have any effect. They basically have logarithmic utility and Cobb-Douglas production functions, and actually any interesting stochastic effects and risk effects, they drop out. So they're not really that much use. And then there's a number of studies, increasing number of studies. The best one by Kai and Lonsek in the Journal of Political Economy. We use impressive numerical routines, and I want to avoid that. So of course I do use numerical routines, but I want to get analytical solutions in order to explain to you the drivers and intuition in such a way that you can actually use it for teaching. So let's look in a framework, and to get these analytical solutions, we use something I won't talk about at the moment, but we use something which is very commonly used in physics, and they're called perturbation methods, and also something called the method of multiple scales. And then we can actually solve these models analytically rather than having 2 or 3 nights of the computer running it. So we're going to have a model where we separate the aversion to risk. So policymakers have an aversion to risk, but that's different from the aversion to intertemporal fluctuations. So if you want, we use Epstein-Zinn preferences. So we actually, in fact, because there's a lot of evidence that people have a preference for early resolution of uncertainty, which really requires the coefficient of relative risk aversion to exceed the coefficient of intertemporal inequality aversion, or if you want to exceed the inverse of the elasticity of intertemporal substitution. So we're going to use something called recursive preferences. And then we allow for a lot of climatic uncertainties and a lot of damage uncertainties and a lot of uncertainties about the future growth of the economy. And to do that properly, we need to model the fat tail, or at least tail risk. We're actually not going to allow for fat tails, but we do allow for skewed risks. And so the distributions are very skewed. That's important because they are, and they're particularly more skewed in the longer run. So for example, if there's an increase in the stock of atmospheric carbon, then eventually, that's the greenhouse effect, temperature will increase. But the uncertainty about that becomes much bigger over the longer run, the more years you wait. And these distributions, the longer distribution, are much more skewed than a distribution after, say, 20 years. Allowing for those skewed distributions, for this tail risk, has huge effects on the cost of carbon. So typically these things, this is quick review to give you a feel for it. typically the price of carbon, and this could be there could be a carbon tax, or it could be a price of a competitive in a competitive market for emissions, is always proportional to this thing called Y, say the economic activity, GDP if you want, or aggregate consumption. And why is that? Is that almost all integrated assessment models of the economy and the climate assume that marginal damages are proportional to GDP. And then typically these mu and phi theta are just, as will become clear later, they're just marginal damage coefficients. And then, so you have to discount the marginal damages with some rate of interest, some rate of discount R star, and I will discuss it in a minute. And then you have lots of corrections for other risks, which I will discuss in a minute as well. But basically, if you look at this, if you eyeball these type of equations, they're just like asset price equations. So in a sense, like the price of a share or a stock is the expected present discounted value of all future dividends. And if you assume that dividends are proportional to aggregate consumption or aggregate output, then you get the same expression for the share price as I've given here for the social cost of carbon. But the social cost of carbon, or by setting the carbon price equal to the social cost of carbon, where the social cost of carbon is defined as all the present discounted value, the expected present discounted value of all the future marginal damages resulting from emitting 1 ton of carbon today. So really, you have to take the present discounted value. You emit a ton of carbon, then temperature will go up a bit more in the next 5 or 10 years. It will go up a bit even more in the next 50 or 100 years. These higher temperatures will affect health. They will affect total factor productivity. So they cause damages, and we need to take the present discounted value of those damages. So in that sense, a price of carbon, I'm still in a one sector model, are just like asset prices, just like a price of a house is the expected present discounted value of all future rents you can get on the house. This is the price, the social cost of carbon, or the optimal carbon price is like that as well. So what does that discount rate look like? So here's a nice simple expression, but I will unpack it to make it a bit easier to interpret. So this is the unpacked version. So this is the drivers of the discount rate. So the first thing, if you think about it, is that the first term is the rate of time in patience. So there was a huge debate in the early literature on climate economics, maybe 10 or 15 years ago. And then William Nordhaus would have put the utility rate of discount equal to 1.5%. And Nick Stern would be following Frank Ramsey and said discounting the welfare of future generations is unethical. So he would set it equal to 0.1%. So therefore, Nick Stern, Lord Stern, the Stern Review, had a much lower rate of time in patience, lower discount rate, and therefore he would advocate much higher carbon prices than Nordhaus did. So Nordhaus's carbon prices have on the whole been fairly modest. And the original part of the debate was about that. So that's the first term. The second term looks a bit like a Ramsey rule or an Euler equation or a Keynes-Ramsey rule. So basically, G is the growth rate of the economy. So if the growth rate of the economy is very high, then that means the future generations are quite rich. So that means relatively to current generations. So then you have to use a higher rate of discount, and you price carbon less because the discount rate is higher. And why is it? Because current generations think, well, future generations are going to be much richer, so let them do it. Basically, if you want, the marginal utility of consumption today is much higher than that in the future because of this growth rate, and then they prefer consumption rather than doing something about the climate. So if you're in fast-growing economies, like maybe developing economies, then they would have a higher G, and they would have less appetite for fighting the climate. Now, this parameter gamma, that is just the inverse of the elasticity of intertemporal substitution, or it is, if you want, the aversion to intertemporal fluctuations. So if gamma is very high, then you care a lot about inequality between generations today and generations in the future. So this gamma G term basically says it's I call the rising affluence term, that if future generations are getting richer than current generations, and if you really care a lot about it, then you have to price, you have to put a higher rate of interest, and then you price carbon much less. The third term is just straightforwardly just a growth correction term, because marginal damages are growing in line with the economy, so you use the growth corrected rate of interest. Then the fourth term, we all know and love. That's a term due to Miles Kimball, and it's called the prudence term. So you see that if the volatility of the economy, let's call it sigma square k, the volatility of the say the total effective productivity, if you want, and it rises in eta, there's the coefficient of relative risk aversion, and 1 plus gamma corresponds to the coefficient of relative prudence. So really, this is better safe than sorry. So if the economy is very volatile, people dislike negative shocks more than they like positive shocks. So it's better safe than sorry. So they use a lower rate of interest and price carbon more vigorously. So this is a term which has not been quantified by Lord Stern, but he made a lot of noise about this when they did it, but they never actually quantified it. Then the next term is what I call an insurance term. Anyone who has done finance will recognize that, and then you might even put a beta in front of it, a climate beta. But as I said, all of these models, they have a climate beta of 1. So what is it? So if you think in future states of nature that the damages are high, then typically the economy is doing very well as well. So really, what you're saying is that that it's a good insurance device. So when just when marginal damages are high, the economy is doing very well, and the marginal utility of consumption is low. So you really can afford to do something about it. So that means you use a higher rate of interest and you price carbon less vigorously. So this insurance term tends to dampen the price for carbon. And then the last term is just that we know that once carbon is in the atmosphere, a large part of it stays forever. But a small part, say maybe, so it's about 20% stays forever, but the other 80% decays. So what does it mean? It gets absorbed by the oceans. Typically, because the oceans is the largest part of the surface on the planet. So and the more of the carbon gets absorbed by oceans and other maybe forests and things like that, then the higher the discount rate you use, and therefore you have to, the problem is less big, so you have to price carbon less. So notice also that if you have elasticity in terms of substitution equal to 1, or in intertemporal aversion is 1, then this whole term drops out. So the Golosov et al. Model, this is the most used model in climate at the moment, just has R star is rho plus phi. And this whole term drops out, so uncertainty in the economy has 0 effect. So what you see, the net effect is that if you have more volatility, if this aversion coefficient is bigger than 1, then you have a low rate of interest and you price carbon more vigorously. So here is an issue in the economics, climate economics literature. They assume that that IIA term, if you want, is bigger than 1. So that means that the elasticity and temporal substitution is smaller than 1. But in the finance literature, they use the opposite. They think that IIA is less than 1, because they think that so there is a debate that if you quantify it on the markets, you get a different result than if you use ethical considerations. I will come to that later. So and then if you look at this formula, you may get correction terms. So I'll talk what delta key is a multiplicative correction term, which allows for the fact that temperature is very volatile. Delta lambda is a correction term to allow for the fact that maybe damages are very uncertain. Delta ck is a term that allows for hedging, so that maybe the shocks to the temperature and the shocks to the economy are correlated. So rather than going through the math, I quickly give you the intuition for that. So here they are. These are these disgusting terms. You try not to look at them. But if you have temperature volatility or climate sensitivity volatility, then the result is that it only pushes up the price if the relative distribution is right skewed, or if damages are more convex. And so the effect, the upward effect on the carbon price is particularly large if temperature or the sensitivity of the climate to the carbon stock is highly uncertain, and if there is a lot of tail risk, if the distribution is skewed to the right, which it is. Damage volatility, so that's the uncertainty about shocks to the damage ratio, only has a direct effect on the carbon price if damage shocks are skewed. So many people found this in these Monte Carlo numerical studies. Monte Carlo studies are highly misleading. And they said, oh, they're very, very small. And I think we can show that they're actually analytically, they should be zero. So that they were small was just a numerical aberration. But of course, shocks to the damage ratio shocks to damages tend to be very skewed. And then there will be an upward effect on carbon prices. So these are the two fairly standard terms about uncertainty about the climate system and uncertainty about damages. Now notice in these mathematical terms, you see this new key and new lambda. So what we actually model them as mean reversion processes. So typically these shocks take many years to have their full effect. So when you increase the stock of carbon, when you emit, it may take decades or even centuries before the temperature has increased fully to its final level. So you have to allow for this mean reversion. So and similarly for the shocks to them. And also when you have a damage, for example, it may go quick. If you have a flood, then you can flood a city, and then there will be a big, the damages occur in the next few years. But some damages are much more slow. So if you look at the damages from I might move a bit, and I think it'll be fine. Some damages take many years. So if you have damages to crops or damages to forests, they take maybe 10 or 20 years. But these time scales are important, and they're important to calibrate them and to look at your proper results for them. So now we look at these hedging shocks, and I think so. You see here the formula, but that's not important. But what you see is these rho k key and rho k lambda. So these are these correlation coefficients. So it's only if shocks to temperature and the economy are correlated, or if shocks to damages in the economy are correlated, that there is an effect. This e-test risk aversion, which you're going to assume to be bigger than one. So let's tell the story. So normally, suppose at the future states of nature, asset returns are typically negatively associated with temperature. So you could say that this temperature beat is negative. So then it pays to invest more in fighting global warming and push up the cost of carbon. So for example, if you have industry selling winter jumpers or heating systems and things like that, then they will go out of business. So they don't like the temperature going up, so they will be big advocates for pricing carbon vigorously and for fighting climate change. Let's say if you're south of London and you live in the chalky coasts of Sussex and Kent, there they make the best white wine and champagne, better in France nowadays. So these guys say, no, bring on the climate change. We love it because the returns on our wine industry in Sussex are positively correlated with global warming. So their temperature beta is positive. So that means that according to this formula, they want a lower cost of carbon. So it basically means whether this rho is positive or negative. It depends on whether your effects, whether the carbon price adjustment is going to be lower or higher. So that's exactly what I did in these two bullets. And it's the same thing with damages. So if you have shocks to the damages, then that typically you would say, well, if the damages are very high, then that typically it would be in future states of nature will be associated with lower asset returns. So then the damage beta is negative, and therefore obviously you will want to do more about fighting the climate, and the cost of carbon is pushed up. So again, there are exceptions. If you come from Rotterdam or the Netherlands, they love it when there are damages. So when there is a big flood, or when there is the dikes are being broken, then all these Dutch companies, these salvage companies and these companies which make water defenses, they see their asset returns go up. So indeed, those guys, they are very much against fighting climate policy. They actually benefit from it, and in that case, they want a lower price for carbon. So all I'm saying is, these are just 4 bullet points, not meant to be realistic, but to give you the type of things that are more important in the disaggregated economy, to understand which sectors are maybe in favor of doing climate policy and which sectors are less in favor of climate policy. So here you see what happens. Yeah.
Yeah, just can I ask a question here? Just want to understand better here. So here, the correlation between the average return of a different asset could be either positive or negative, right? So in your model. So, but what about this uncertainty? The uncertainty is the climate change increase the uncertainty of all the risk of all assets?
Yeah. So what we need much more is what the field has not done yet, but what we should be doing is trying to investigate those risks at the sectoral level. What are idiosyncratic risks? What are sector-specific risks, and what are economy-wide risks? Because they will have large effects on the way we should conduct our climate policies. So today I haven't got those empirical results with me. I've got some, but I think they should deserve much more work and to do it properly. But they have big potato effects on the way we conduct climate policy. I'm not sure whether that answered your question.
Yes, I think you have answered a part of it. Yeah, because I'm just thinking here you talk about the climate change, how it affects the average return. But I'm thinking about how it affects the volatility of this return. Whether it
okay. Oh, now I see your point. Yeah. I see now exactly what you mean. I have not done that here, but I see this is a very exciting suggestion you're making. So I do allow it in the next paper. So you may have catastrophic disaster shocks, think like Robert Barrow, for example. And then you might say that the probability of these disasters occurring may increase with global warming. And that gets close to what you say, that the volatility or that the tail risk, if you want like that gets worse, either with damages or with temperature. So one thing I have allowed for is to allow the probability of disasters occurring, or indeed the volatility of disaster shocks to the economy, to be a function of temperature. But what you're now suggesting as well, they may be, of course, affected by the damages or the cat. So they are affected. That if there's a disaster, if there is a kind of a climate disaster, they will affect in these models with tipping points. They will affect both the volatility and they will affect the probability of these things occurring. So that goes quite a lot in your direction. But that's a very much of an ongoing research. It's exactly the frontier where people are working on at the moment. Not many, incidentally, but there are 2 or 3 people working exactly on these issues.
Okay. Thank you.
Including myself, but but it's tougher because you can see it becomes highly nonlinear, and you have to think about it. Now, the follow-up paper to this American Economic Review paper from the Bremer is exactly dealing with this issue you're talking about. So I just written down your comment about the damages themselves affecting the volatility rather than temperature, and I think it's a very valid point. Yeah, thank you. Okay, so now a bit of calibration. So people often so the calibration, it's a funny world, you see, because you have all these science models. So they have hundreds and hundreds of scientists, and they have models with thousands of equations, and there are about 8 or 9 teams in the world, and they produce all these very controlled runs, if you want, impulse responses, and then people make small models trying to replicate what these science models are saying. So it's really an exercise in model reduction. So if you look at the gray region on the left, that's the 5 and 95% confidence interval, or the bounds, if you want, of all those simulations in a very famous study by Joost et al. They haven't changed very much. And then typically the best fit is this black line. And then you can actually use the probability distribution to characterize it as well. For this, I just used a very simple one, namely the red line. And then we can actually fit that uncertainty as well. If we allow for more than one difference equation, maybe 2, 3, or 4, like the Joost et al, the black one has 4, we can mimic the black one identically, but I'm just doing this for simplicity. So, and it's the theory we have just extends very easily for that. This is not so important. What's important is this one. So this is the effect of doubling the effect of doubling the carbon stock, doubling the stock of carbon in the atmosphere. And then what happens to temperature? So the left-hand diagram is what happens after 40 years. And the right-hand diagram is what happens after hundreds or thousands of years, the long run one. So you see first that the left one is the short run one, the short run is 40 years, is very symmetric, whereas the right one is very skewed. And it's this skewness that is really kicking up the price for carbon. So we fit a kind of, in discrete time, you would call an AR1 process, and then we take a power function of the AR1 process to allow for the skew. In continuous time, an AR1 process is called an Ornstein-Uhlenbeck process, and that's what we use. It's well known in finance. And so then we get our temperature fit is the red one. So we match the black one of the models very close. Yeah, so that's the mean of all these models. That's a remarkable fit. And then the best one on the right-hand side is much more difficult model, was done by Pindag. And he models it with Robert Pindag. And he models it with a gamma distribution. And you see that our distribution, the red one, does much better. It's a one equation model of this. Well, it's then with a power transformation and with mean reversion. And then we can explain both the shorter run and the very long run fix. So notice here that the mean temperature is about 1.5. And here the mean is about 3. So that mean thing is called the equilibrium climate sensitivity. But look, that here is the median is much lower than the mean. So that means this is a big tail to the right. So we have to allow, if you don't allow for this thing changing over time, which nobody seems to do, then you're really making a big mistake quantitatively in terms of estimating the price for carbon. So that's what we do. So here you see this climate, the IPCC reports, and they give all these ranges. So this is called the TCR. These are probability distributions. These are probability distributions. This is the TCR, the transient climate response, and this is the ECS, or the equilibrium climate sensitivity. So here you see it's between 1 and 2.5 degrees. You see, this is what they find, all the scientists, and how close our model is. This one is not so good, but it's not, basically the idea is not that 0.6 is different from 0.054. It's so small, it doesn't matter. Look, in the long run, it's 2.4 and 2.5, that's much more skew. So the fit is remarkably good, and that's what we use. So these are the damage ratio uncertainties. So this is a guy called Richard Toll, and he's done a lot of these meta studies, which then William Nordhaus did them again. And he said there's too much double counting, and some studies are not so good and other studies are very good. If study is good, they get a big circle. And if they're not so good, they get a small circle. So the size of the circle says something about the reliability of these studies. And then you see that the damages is a fraction of economic activity, how they increase with temperature. So maybe they're about very small. But if we do go up to 3 degrees, they can go be much higher. Notice that they're all quite modest. People like Marty Weissman said they should be much higher. Anyway, we estimated, so these are all various estimates. In the end, we go with the red one. That's ours. And then we have these confidence intervals. So we allow for the uncertainty. So this is the plus or minus 2 intervals, plus or minus 2 standard deviations. And then here we take a more convex variance, where this rises more sharply, if you want. So anyway, that's our model of damages. And then if you look at the rest of the calibration, the risk aversion is quite high. It's 4.3. The elasticity in terms of substitution is 2/3. The rate of time patience is quite high. We have either used asset volatility is 12% per year, or consumption volatility is 1.5% per year. We can explain the risk premium, which is the 6.4%. So that's the difference between the 7.2% on assets, on risky assets, and the 0.8% on safe bonds, if you want. Trend rate of growth is about 2%, et cetera, et cetera. And then this last thing is the flow impact of global warming damages at 2.07%. That's very much in line with what people like Nordhaus have done. So it's actually on the modest side. So just to give you a feel, the type of things you can do, we split up the stuff that's normally reported, which is the first line, the deterministic cost of carbon. So it's dollars per ton of CO2 emitted. And then we allow for all these different markups, a markup for economic risk, a markup for a risk about the carbon stock, about climate sensitivity, about damage ratio, and the total one. So the base is really like Nordhaus. So he finds about $12 per ton of carbon. But see, if you're not allowing for all risks, if you allow for all the risks, it should be about 40. So 40 is much bigger than 12. There's a climate risk about 250% extra markup you're missing if you're not allowing for uncertainty. So I think it's important because most of these studies report these deterministic ones. A lot of it to do with economic risk, some to do with temperature risk, but they're all going in that direction. So if you if you then look the last column, which I'm trying to see if I can show you. No, I can't do. The last column is the one for Stern. So he uses these more convex damages. So he gets much higher price of carbon, as I said before, not 12, but $87 per ton of CO2. But if you, and then it almost doubles if you allow for risk. So for various reasons, which I won't go into there, you get all these markups for the temperature uncertainty, damage uncertainty, because it's actually very convex. You get a negative effect for carbon stock uncertainty. I didn't mention that in the talk, but it's very small, so it's almost negligible. So so what you're saying is this is an exercise two ways. You can very quickly, on the back of an envelope almost, show the different effects. For example, the most famous study is by Golosov et al. So they, in the econometric one, they get a $19 per ton of CO2, and there's almost no adjustment for risk because they have logarithmic utility. Economic risk doesn't affect it at all, but they do get climate sensitivity risk and other risks. So you can extend this with what we just discussed. If you allow for macroeconomic disaster shocks, and you say that some of these disaster shocks are temperature related, or as the question just asked, disaster related, then you can make the probability of a disaster occurring increase in temperature, or maybe increase in the damages that have occurred, the disaster that have occurred. And that's a kind of uncertainty that you would do on top of the normal geometric Brownian motion. If you allow for that, it's much better from a macro finance point of view, and you get that. So effectively that formula, then you get an extra term here. The discount rate is a standard in asset pricing, I think, but more importantly is this term here. So you get an extra term here. It's positive, and this lambda E is the sensitivity of the. It shows how much the probability of a disaster is affected by global warming. So if the probability of disasters increases with global warming, you have to internalize those as well, and therefore you get this extra term. Okay, so let's move on to what I really want to do. So I come now to the second part of the talk, which is the paper which has been announced. But I had a bit of a long introduction, but I wanted to do it. So now we're going to do something that has not really been done. So people are moving to multiple sector models now. So for example, in macroeconomics, when it's not about uncertainty, so various students of mine, but now increasingly central banks are doing it as well. And they're using these Gertler-Gerardi models to allow for financing constraints, financial accelerators. And then the idea is that maybe transition risk, so uncertainty about the policies being implemented in the future, how they affect things like asset prices, and then they might actually lead to a tightening up. Uncertainty about climate policy being implemented in the future may lead to these financing constraints, borrowing constraints to bite more vigorously. I'm going to put that to one side, but I am going to look to a more long-run two-sector model. Well, one of the sector is green, and the other sector is brown, and the brown sector is one sector which uses fossil fuel, coal, oil, and gas, and therefore contributes to global warming. So if there is a deterministic world, and there are no adjustment costs, then you immediately switch the capital to the green sector and there's no problem. But of course, there are adjustment costs. Full specialization takes time. So even in a deterministic world, it takes a long time to switch. Now the point is that in a stochastic world, people want to keep open the brown sector for some time for a number of reasons. One reason is the brown sector may be highly profitable, and it helps to finance the green transition. The second reason is that maybe, depending on how the shocks are distributed, the brown sector may give you some hedging opportunities, which you don't get if you fully specialize in the green sector. So we were in this paper trying to address the issue, whether there may be a trade-off, either in the short run or the long run, between on the one hand, the desire to diversify your assets, and on the other hand, your desire to fight global warming and to have a green transition. So now we have a more richer model of negative effects of global warming. We have the usual one we just discussed. We have that temperature negatively affects total effective productivity. That's the first one. But secondly, we will also allow that the likelihood of climatic macro disaster risk increases with temperature. And then thirdly, we can also easily allow for the fact that that temperature may lead to destroy capital. So it might have an increased depreciation rate of capital. So there are not just one, but there are three reasons to price carbon. I think for the purpose of these slides, we will focus on the first two. So we will focus on macroeconomic disasters, which may be related to temperature, and we will focus on the standard production damages. And then we're going to kind of look how to price carbon, how it speeds up decarbonization of the economy, and how you get the structural transformations. So we're going to, in the course of doing that, I will also discuss the effects on the carbon price, but also on the save rate and on the share prices of these carbon-free and carbon-intensive industries, or these brown and green industries. So our interest is well, we want to see the economy has to switch out of these dirty products into green products. They have to kind of get rid of oil, coal, and gas and start using solar and wind energy. So we're going to model those explicitly. And our particular interest is to interplay between financial considerations and policies to mitigate climate change. So the key questions is, does financial need to diversify, does it help or does it frustrate the fight against climate change? And how does climate change affect the prices of green and dirty assets? That's the question I get asked most by pension funds if they ask me for my advice. So we're going to show a subtle dynamic interdependence between the financial goal to diversify assets and portfolios and the environmental goal to cut emissions. And I don't have enough time to look about policy uncertainty, transition risk, and stranded assets, but that is a follow-up paper. So what does the model look like? First in words, we have a green sector, we have a dirty sector, we have adjustment costs because you want to have some sluggishness to it. It also allows you to get a better explanations of asset prices. And we actually also allow for adjustment costs not only over time, but also across sectors. So you could alternatively assume that capital is putty clay, that is, once you've invested in a particular sector, it stays there forever. So that's irreversible. But what we're actually assuming is that the capital is that is costly to shift capital from the brown sector to the green sector. And the growth in capital needs sector is subject to these Barrow-style macroeconomic disaster shocks. And we split up his data set into macroeconomic disaster shocks and more climate-related disaster shocks. Then we have these preferences which separate aversion to risk from aversion to intertemporal fluctuations. We allow for leveraged dividends, and that allows us to calibrate a high equity premium and the low risk-free data in the data much better. So temperature is now a simple linear function of cumulative emissions, and emissions are proportional to fossil fuel use. So that's the model. So a preview of the results. You diversify until there is a balance between green and brown capital, and I will discuss what balance is when I give you the simulation. So that is basically 50-50, or it is a particular percentage which comes out of the field, but you diversify. Environmental perspective is, well, no, we don't want balance. We want to run down the carbon-based capital stack completely. Now, then we show numerically that if you have these damages, these low damages of William Nordhaus, you never run down the carbon-based capital stock completely. But if you have much more severe damages from climate change, then you will run it down completely. So on maybe a Stern or a Weitzman type damages, you will do it. So the conclusion is that diversification considerations can prevent driving the carbon-based capital stock to zero. Okay, so the model, I will not talk about it too much, but you will see here various two sectors. One is a green sector, two is the dirty sector, and they have conductive production functions. There's a negative effect of temperature here in TFP, depend on capital or fossil fuel use and labor. Here it's a bit of an AK style, so this is aggregate capital stock. And here's the same, so you can rewrite this, what we got here, like that. And then we're going to assume that the green, well, it's not necessary, but this particular slide, we assume that green and brown capital are perfect substituting consumption, and we show results when they're not in an appendix. So these look in continuous time, the two models for the capital stock in the green sector and the capital stock in the brown sector. So you have these are Brownian motions. So you have these geometric Brownian motions. These are the Poisson shocks, the Barrow-style disaster shocks. There are two. One of them are economic, think of a war or a recession, and the other are climate related. So the effect of global warming may be a tipping point or something like that. And there you get a disaster shock. And these are the size of the losses, LC and LE. And you have the same thing also in the brown sector. So you see here normal investments, and then there are the normal adjustment costs, Hayashi style adjustment costs. So the only novelty is that you can take capital away from the brown sector and put it into the green sector. Minus R here, plus R here. To do that, you have to pay these the intersectoral adjustment costs. And then you see that the depreciation rate of capital may increase in temperature as well. So this is what we do, this is what we calibrate, and that's what we play with. So this is temperature. The most recent insights are that they are very well described as a function of cumulative emissions. That's actually what the IPCC does, so that's what we do here. So temperature is a function of cumulative emissions. Initial temperature is about 1.1 degree, and we allow for some uncertainty, which we calibrate from these climate science models. If you could possibly allow this diffusion coefficient, this volatility, to be not constant, but to increase in temperature, or as the question asked, maybe to be a function of damage shocks. So to answer that question better, so now we have tipping points of view, but sometimes you could say that there is a cascading of tipping points. So your question is really speaking to the possibility that a damage shock, a damage disaster might lead to more unleashing nasty positive feedback effects in the climate system, or they may even unleash other climate tipping points. So that's something one could talk about as well, but I won't talk about here. But that's a separate issue, very interesting, but it's not on this today. So we assume that dividends are proportional to, say, consumption to the power of 3. So that's really like a leverage thing, and that allows you to calibrate things well. We have recursive utility. So we distinguish risk aversion from the inverse of the elasticity of intemporal substitution. That's what it looks like. And this is a horrible, you don't want even to look at that, but it's a horrible Hamilton-Jacobi equation. It's the reason I'm showing you only is to show that it depends on time, the capital stock in the green sector, the capital stock in the dirty sector, and on temperature. So that it should be easy to find a value function, but that's very difficult. So what we can actually show for this model, that we can reduce the state space to 3, namely temperature, and then the share of dirty capital, K2 over K1 plus K2, and temperature. So in actual fact, it's not a 4-dimensional problem, it's a 3-dimensional problem, and that our computer can manage reasonably well. So we can do runs, and this take us about half a day rather than maybe a couple of weeks. So this is very helpful. So what you see is that if you look at the optimality conditions, some of them are already easy to interpret. So you see that investment rates are proportional to Tobin skew. So if the Tobin skew in a particular sector, the green Tobin skew, and Marshall Q equals average skew. So if the share prices are very high, then you will attract investment. And the Tobin skew, and also if you look at this equation for R, that's relocating how much you relocate capital from the dirty sector to the green sector, so that if the green sector has a much higher share price than the brown sector, then that will really incentivize people to shift capital from the brown sector to the green sector. These conditions just say don't even look at the mass, but all they're saying is that the marginal product of fossil fuel, like the one here on the right, equals has to equal the cost of fossil fuel plus a carbon tax. And that comes out of the model. Whereas here, the marginal product of renewable energy just has to equal the marginal cost of renewable energy. Notice that these marginal costs are not constant. So there is an upward sloping supply schedule. And then this TF is the optimal PGUV tax, so it's a bit like the social cost of carbon. So this is what I already said. So this is the way the model is calibrated. Now it's much better than the aggregate model I discussed. I started off with the AAR paper. We still have a risk aversion coefficient of about 4.4. It's quite high. Now we have an elasticity of interval substitution of about 0.6. And we have a type preference rate, not 5%, but only 1.5%. Now this looks much better. And the reason it looks better is what we teach our students. Epstein-Zinn is not enough, but if you have Epstein-Zinn and disaster shocks or Barrow, it goes reasonably well. An alternative to resolve the asset pricing puzzle, equity premium puzzle, is to allow for habit persistence. So we could have done habit persistence well, but we've done this and it works reasonably well. So then we calibrate to the world economy. So that's about $76 trillion in the beginning time. We have an initial share of dirty capital of 94%. We calibrate, glean that from the data, and then we gradually start fitting all the other stuff. We have you see price elasticity of energy supply, the adjustment cost parameter, and the whole paper discusses at length how we fix that. So, but let's give you some inclination of what these things are. So the share of energy is 6.6%. We match cost of fossil fuel and green energy to these prices in the market. So we match the risk-free rate of 0.8% and equity premium of 6.6%. So and a Tobin skew of 1.58. We match the volatility of consumption in the global volatility of global consumption, et cetera, et cetera. And we take the transient climate response to cumulative emissions. So temperature goes up. For every trillion tons of carbon in the atmosphere, temperature goes up by 1.8 degrees Celsius. And then we allow for some technical progress. So that's a steadily declining emissions intensity. So here are our types of damages. So these are the Nordhaus damages. So you show that the damages are a decreasing function of temperature. These are these disaster damages. The probability of these disasters increases in temperature. And further, this is that the depreciation rate, the amount by which capital gets destroyed, increases in temperature as well. So Barrow and Ginn, in that 2011 paper, said that if you look at the disaster data set, the average consumption loss, if a disaster strikes, is 20%. And then they said they have an annual disaster risk of about 3.8%. So then they can back out you call it intensity of 0.088. And then they can also fit a power distribution to these shocks. And then you get power distribution parameter of 8. So we now have to do something different. So we take these disaster shocks from this MDAT database over the period 1911-2015, and then we split up some of the sample in macroeconomic disaster risks and the other sample in macroeconomic but climate-related disaster risks. So the disaster risk, say the probability the disaster hits within the period of a year, varies over time. So we find that for these particular disasters, the jump size of climate disasters is about 1.5%. And we can also fit a power distribution. So we fit basically those shocks. So we fit both normal Barrow style macro disaster shocks and climate-related disaster shocks. And the interesting feature here is that here's an externality to be internalized, because if we contribute to global warming, we don't only destroy total factor productivity or we destroy the capital stock, but we also increase the likelihood of these disasters. This is very important because the IPCC in their last report, the last two reports, but particularly the last report, highlights the fact that global warming really leads to more climate disasters. That's the most important thing to have. So this is really very topical because it really captures the concern of the IPCC. So you see here, yeah.
Can I ask you a question before you move on? So here, when you talk about this climate disaster risk, it is just the macro risk, right? There's a common shock to all both sectors in your model.
It did, yeah. In this model, we kept that the same, but of course that could vary. So we calibrated this to be a common shock to the economy. So like if there is a flood, for example, or a storm, it doesn't distinguish whether you have a green factory or a brown factory.
Yeah,
but that's just because we didn't know how to calibrate it at this point.
Yeah, then your models, do you have this sector-specific risk and how you set the correlation between them?
Yeah. So we do, good point. So we do allow, and I will show you in the simulations if I get around to it, we do allow for correlated risks in the geometric Brownian motion. But in a sense, you have a good point that these tipping risks are perfectly correlated. But of course, we have done runs where they're not perfectly correlated, so we can play with that as well. Yeah. So the way we look at correlated shocks is look at correlation of the normally distributed shocks to the two sectors.
Okay.
But that's fairly easy to allow for to look at that as well. Yeah.
Yeah, then I'm just wondering, can you just intuitively explain how to diversify the risk in this setting, under this setting of the model? You have two sectors, and then now you are considering the risk diversification.
Yeah. I will show you. Yes. I will show you a diagram where this will come out in a second. I'm almost there. So let's ignore this. So I'm going to do it now. So let's go to the results because it makes it all a bit more. So show some simulations. So we're starting in 2020, and then I will discuss those intuitions. And then we start about $26 per ton of CO2 for the DICE damages, and we have if for climate disaster damages it would be much higher. So the optimal carbon tax rose in line with the economy. But if the damage are more convex, carbon tax will rise faster in the economy. So for example, you may look at this. So there are always two panels, left panel and right panel. They are two different models. So the left panel is where we focus on the temperature affecting total factor productivity. And the right panel focuses on temperature affecting the likelihood of disasters. So they're just two different ways of modeling damages. So what you see here is just the optimal carbon tax goes over time. It just rises roughly in line with the economy. And these are the 95% bound. So this is okay. There's nothing much to say, but this is roughly what they should be. And then on the right-hand side, and then if you look on the bottom panel, the normalized carbon tax, which is basically the carbon tax correcting for growth, rises a bit over time. That's because the damages are mildly convex. Here, they drop over time. So here you look at one second. I've got hay fever, so this is the problem. So on the right-hand side, we look at the likelihood of disasters. And once these disasters have occurred, then the normalized, so this is a decreasing function. So they grow less fast than the growth rate of the economy. So now I'm going to try to get into this intuition, the intuition you wanted me to talk about. So I'm going to give you a plot of the median optimal evaluation, the medium optimal carbon-based capital for a number of scenarios. So I'm going to show you these. So if you look at the first one, the gray dots in panel A, then we have no damages, and we have perfectly correlated shocks, geometric Brownian motion shocks. So in that case, if there's no damages, there's no abatement motive, there's no climate fighting motive, and there's no diversification motive, because the shocks are perfectly correlated. So let's look at these gray dots. So then you see that the gray dots, that means that the share of dirty capital just stays at 94%. There's no reason to change it. There's no diversification reasons, and there is no climate reason. So you just keep it at 94% initial level. It just stays flat. Okay, then we go to the second scenario. So let's now say that we don't have damages. We don't have climate damages. No need to worry about climate. But we do have a worry to diversify, because the shocks to the Brownian motion shocks are uncorrelated. So then it may be worthwhile, if the variances are the same, then you would want the share of dirty capital go to 50%. That's the result due to Cotray. So then you get the black dots. So if you then look at the next page, you look at the black dots, you see that this, rather than the gray dots, it stays flat, you gradually go down to 50%. So this might happen if the shocks are not correlated, and this is the shocks are perfectly correlated. And you see this here again. So this gray area in panel B is what you would call the diversification motive. It's a difference you get between if the shocks are perfectly correlated and if they're uncorrelated. Now we go to the third scenarios where we have perfectly correlated shocks. So there's no need to diversify, and we allow for global warming damages of the type in DICE. So we have an abatement motive, but we don't have a diversification motive. So now we have to look at the gray solid lines. So here you see, there you go, there's the gray solid line, there we go. So basically you bring it down much faster than so one, you bring it down because it's without the abatement motive, it will be flat. You bring it down, and you bring it down at some point completely to zero. So here you have the full transition. You see it takes time because of the adjustment costs, and you bring it down. So this is a case, this is the dark gray scenario where the shocks are perfectly correlated. The last scenario is where you have an abatement and a diversification motive. So then you get the black solid line. So in the short run, the abatement motive and diversification motive go together. So you bring it down more than the dark gray line. So it goes faster. But then after you've passed this point, 50.5, the black line is above the dark gray line. So then the abatement motive and the diversification motive frustrate each other. And therefore that in the long run, you don't bring down the stock of dirty capital to zero, but it stays at about 20%. So therefore you can see that that in the short run, diversification and abatement go together, and in the long run they go against each other. And more generally, you see the point that although you really, you don't bring down the capital stock immediately to zero, it's just too costly. But you may not even never bring it down to zero because you keep over the dirty capital stock, perhaps to allow for some, because of the hedging advantages. And that's one of the main part of the story. So I hope that diagram explains it a bit. So this is our story. So
yes,
then we go. Yeah.
Yes,
I hope that's an answer to your question.
Yeah, it's almost. Here I have one question here. So intuitively, so the black line seems to me should be the convex combination of these gray dots and the green solid line.
Yeah.
But it's interesting. It seems to be after year 2100, 2100. Yeah. Okay. But before that,
Yeah.
seems to be not the convex combination.
Yeah. The reason is very well spotted. It's not wrong. It's meant to be like that, and the reason is that these effects are kind of non-monotonic, and I will explain that in a table later on. So there is something in between 100% diversification and 0% diversification. There's a non-monotonic effect, and that's explaining why it doesn't go in the way you suggested. And I think it's best to show it to you. If I get to show you the table in a minute, then I think it will click. Okay. I'm not doing better than this at the moment, but I will come back to this point.
Okay, thanks.
So what we're really saying is that with climate disaster shocks, the damages are bigger. So the abatement motive dominates the diversification motive. So hence the dark gray area is big and the carbon-based stocks run down to zero, even with uncorrelated shocks. But if you have a higher instantaneous correlation between the two shocks, that curbs the benefits of diversification. So you lower the value at which the share of carbon-based capital stabilizes in the long run. But you still find that the optimal carbon prices are primarily driven by the abatement motive. They're not driven by, they're not much affected by the diversification motive at all. So the diversification versus abatement affects the speed at which and whether you completely transition to out of dirty capital to green capital. That's affected by that. But the optimal carbon prices, as you've seen, are not really affected that much by that at all. So now let's kind of just give a extra bit of intuition. Yeah.
Can I ask a quick question before we move on?
Of course.
So this is not my field, so I might be getting it wrong, but could the production in the brown sector actually improve the productivity in the green sector, the TSP? So I'm thinking things like, Tesla. The research and development that went into developing the technology was not as clean, but the product that you get out of that is actually improved, right? The way in which it works. And that kind of complements the diversification motive pool as well, right? That you'll want the brown sector not only because you want to diversify, but also because it might actually improve the abasement ports. Yeah.
I think this is an absolutely excellent question, and I recognize it because we've been told this by a referee. But we didn't do it because this is basically an illustrative paper where we try to highlight some new mechanisms. But I think the mechanism you just highlighted is extremely important. So at the moment we don't have these interaction effects. But I mean, we started off the paper with having a kind of network model of the economy, like with a proper input-output structure, which would allow you to have some of these effects you just mentioned. And I think we have to do that. I would probably make that a separate paper in order to really go into those issues. It's basically ongoing work, so I haven't got much to report on that. And the reason it's ongoing work that we haven't found a way to program that in a nice and easy way yet. But we can program it, but it's just highly costly. So we're still working on the topics, maybe not quite the way you said, but to look at these interactions between the production sectors, allow for network effects, but also allow these that you may need the brown sector to produce the green sector. But I haven't got anything to present yet, but I realize it's extremely important. I'm very grateful for you pointing it out, because it does show that we have to work harder on that. Thank you very much. Yeah, very good point. So to give a bit more intuition, so just imagine that you now change the volatilities. So remember, at the same volatility of the green and the brown sector, these are percentage volatilities. So now imagine that they are a bit different. So imagine that the long run share, the volatility. So if you have a low risk, benchmark risk or high risk, then that will affect the long run shares. So if you look here, this looks a bit awful, but if you look at this diagram, so what you're trying to show is, now let me do the intuition first. If you take climate change into account, the reduction in the dirty sector is bigger if the volatility of that sector is smaller and has a larger diversification potential. So with a low risk, so then you have a high diversification potential, the share of carbon-based capital drops from 66% to 26%. And if you have a high risk scenario, then you have the long run share of capital drops from 33% to 15%. So the abatement motive is biggest in the low risk scenario, despite the share of the carbon-based capital and temperature being higher than in the benchmark. So this is explained in this diagram, but it requires a bit of time to get your head around it. But it does show, for example, if you look at the gray lines, and then you have the gray lines show the high volatility of shocks to the dirty sector, and the light gray lines show there's also low volatility of shocks to the dirty sector. So you have the say if you're dark gray and light gray. So the black is the medium, the benchmark, and then the dark gray is the higher volatility shocks to dirty sector. So you see, if you have a higher volatility of the shocks to dirty sector, you bring down temperature more, and the reason is that leads to that's coming to a lower. You drive down more the share of dirty capital. You drive that down just because diversification demands you doing it. So if you look here, you have the light gray without damages. It normally goes to 50%, but if you have a higher volatility in the dirty sector, you bring down the dirty sector even more. And here, if you have lower risk, it's the light gray potential. Sorry, the low. Say it properly. The light lines, you have a lower volatility of shocks to the dirty sector, so the dirty sector is not brought down as much. But this is, of course, also true if you have climate, if you allow for climate, and therefore you see that how it depends on the relative sizes of the volatility of these shocks. Okay, so if you then look at the asset prices, they are very, so H is what's called in finance the stochastic discount factor. There it is. You can derive it with the usual expressions, and then we get this thing here, and I want to explain to you this equilibrium risk-free rate, and it's very similar to what we see in finance, but it's very similar to what people like Barrow and others get in finance, and people like Campbell and people like that, but it's got some extensions. So you have here this discount rate. So it's a little bit also the same as I did what I started the seminar with. This is this affluence effect, 1 over the elasticity in terms of substitution times the drift term. This is the prudence effect, so we know these things. It's a bit more complicated, but here you see a norm, and that's because it's a summary measure of the volatility of the two sectors, but this is what you get. And then you get a sum of the two types of disasters. You get economic disasters and climate-related disasters. And then this is a type of thing which is well known, type of shock, except that we have the novelty to us that one of these shocks depends on temperature. So you get this is a precautionary effect for precautionary. So basically people are doing precautionary saving because these shocks are volatile. And because there's precautionary saving, and there's a bonds are in fixed supply, the rate of interest must fall in equilibrium. And similarly, this is disaster risk, and that leads to precautionary saving, and therefore the interest rate must fall. And that of course, that means you price carbon more vigorously. So this is the finance interpretation. Completely new terms, it is temperature interaction risk. Which we should not look too much at the moment, but there's an extra term to allow for the interaction between the different types of risk in our model. Okay, so what we actually see here is then that if you want, this just explains what we had. You still have a rate of time patience, you have an affluence effect, you have to subtract the prudence effects, and you have the prudence for the disaster risk effects, and then you have to subtract temperature interaction risk. So if you look at it, this is if you decompose this for a particular year, say the year 2100, but it doesn't matter. You can see how the risk-free rate, how it depends on the different components. And then you see a number of things. You see that the precautionary term doesn't vary much with temperature, but this is the affluence term. It decline if temperature goes up a bit. Then basically the drift falls a bit because the expected. So therefore this falls a bit. More interesting is how this depends on the share of dirty capital going from say 5% to 95% to 5%. So here you see this is the non-monotonic effect I tried to do two questions ago. So it goes from minus 0.19 to minus 0.111, and then it goes to minus 0.19 again. So what you see is that the prudence effect is most negative when you're not diversified at all. And it doesn't matter whether you're not diversified by having too much dirty capital, whether you're not diversified by having too much green capital. In both cases, you have to do a hell of a lot more precautionary saving, and that therefore has to be more vigorous climate action. So it's only when you're balanced, when you're in the middle, that this precautionary effect is fairly small. And this is the reason why when this question was about the convex combination, why it goes the other way around. It's this effect which is doing it. So we can show that if you look at the safe rate of interest, then it falls with temperature, but it first rises and then it falls as the share of dirty capital increases. So when we look at the fact that what I'm trying to point out is this non-monotonic effect, which you can see this bullet here, as the diversification across green and brown reduces the volatility of total capital and aggregate consumption. So that's actually driving the results. So here you can see that the carbon price is also effectively just an asset price. Here I show various other asset prices and excess returns. But let's look at some of these asset prices just to give you a feel for it. So the first thing I want you to look at is the main thing is this top right panel. So you see here that the risk, the rate, this is against temperature. Look at the risk-free rate. So as temperature goes up, there's more precautionary saving needs to be done to prepare yourself for those temperature shocks that are occurring. And therefore, the effect that this drops a lot over time is reflecting the effect that there's an increased need for precautionary saving. The rate of interest is falling in equilibrium to clear the bond market. So what you see, the dark line corresponds, sorry, the black line corresponds to S is 0.9, and the gray line to S is 0.5. So what you see, it depends on the share of dirty capital in a non-monotonic way. So there is a bit of stuff in the paper which I won't discuss too much here, but just highlighting it. There is sometimes an option to convert. So there is in our work we also discuss option value. So the brown and green risk premium turn out to be positively correlated with the share of dirty capital and also the share of green capital. So the asset that is most scarce carries the high risk premium. But if the option to convert is taken off, like in figure 5, the brown risk premium has to take account of this option, and that option is more variable if the share of dirty capital is high and temperature low. So in that case, green assets are less valuable and the green premium is higher if the share of dirty capital is large. So you see some of that here again. I want to move on to this and show you some simulations over time. So this is what we're going to do. Yeah, I'm going to drop this.
So Rick, so you might need to speed up.
Yeah, I'm going to do that.
Yeah.
I realized that. So I'm going to finish with some general comments. So I'll be done in 1 minute. So let's look at some empirical work. So maybe the best study is the study which came out this year in the Review of Financial Studies by Patrick Bolton and Kasperczyk. So they look at stock market returns of carbon-intensive firms like steel, cement, aluminium, oil majors, you name it. And then they show that after you allow for the pharma French factors like size, book-to-market value, etc., that they have to pay higher stock market returns than green firms, which is kind of interesting. So the idea is really that reflects that they're dodgy, risky assets. So the investors are already demanding this since about 2015, not before, demanding compensation for the carbon risk. And so that's a very robust result. They find it also globally in about 80 different countries, and they find not only, so they find evidence for a carbon risk premium, so that if you're a Shell or a steel factory, you have to give higher rates of return to your investors, because otherwise they're not willing to hold your assets, because they're taking account of the possibilities that these assets may drop in value, either when there is a breakthrough technology in renewable energies, or because the governments are waking up and suddenly pricing carbon. And actually, they show that this carbon risk premium is rising over time. There are some other studies which suggest the opposite, but I think this is the best study, so my money is on Bolton and Kasperczyk. So here you see this cumulative carbon risk premium over time. So really what all this is suggesting, and that's what most central banks are concerned with, is the probability of transition risk. So I've looked mostly at physical risks. So that's the effect of temperature disasters, the effect of disasters in the economy, damage disasters. But I haven't really looked at transition risk, the risk that policy may suddenly change. That's a much more difficult exercise, because then you have to solve the model as a decentralized market economy. And that's really where all our current research is at. And maybe I should leave it at that, I think. Yeah. Just as a last point, there's also evidence that also banks are, when they lend money to corporations, there's a lot of detailed evidence that banks now ask for much higher rates of interest for dirty firms than for clean firms. So if you want to get a loan from a bank, and if you're green, you have to pay less interest than if you're a dirty firm. And of course, that's also capturing the fact that banks find these firms quite risky. So there's also evidence for the fact that there is transition risk, which is, of course, happening on a much lower, shorter time scale in the next 5-10 years, rather than the type of physical risk I looked at, which are physical risks are occurring in the next 20 to 100 years. So with that last comment, I'll leave it, and I thank you for your attention.
Yeah, thank you very much, Rick. So now I think officially, so our seminar has already have to end. But I think we can
Okay.
still stay here if you have any questions to Rick. And Rick, would you like still stay with us for questions?
Yeah, a few minutes.
Okay, yeah, great. So any questions so far? Yeah, would you, okay, Tusha first, okay?
No, I'll let Ken go, mine is not important.
Yeah.
You're muted, Ken.
Okay.
Not sure that I deserve that accolade. Thank you, Tusha. Now, I understand this is a very stylized model, and I admire what's achieved in such a stylized model. My question is as follows: when you've got this brown sector and the green sector, can you regard them as both producing energy? So you have basically a submodel of the economy which produces energy, and then that may well feed into other sectors of the economy, some of which are more energy intensive than others, and some of them have more utility value than others. What do you think about this interpretation of what you do, Rick?
Yeah, I think that's an extremely good point. So one way of doing it is to have an energy sector which has typically is done with a constant elasticity substitution between coal, gas and oil and renewable energy, and then to use that aggregate energy as input into a production of for final goods. Doesn't quite capture what you really want to do, but you really want to go, if you wanted to go your direction, you want to allow for transport and maybe electricity, and then sometimes there's substitution possibilities and sometimes there are not. So for example, to change a electricity power station from coal to gas, it requires quite a lot of or to solar even, it requires a lot of extra investments which needs to be taken account of, which we have not done. But I think they're very important. But then the way the substitution possibilities are, say, in the transport sector are different again. So then probably you want to have a transport sector and a power sector, and then let those feed into the final goods production sectors. I think that is a fair point. Yeah. That's a very fair point. And of course, some of the more detailed integrated assessment models do exactly that, of course, but then they don't do any of the stochastics. So there is a line of work there. And particularly when you go into this more, the nitty-gritty of how these things work out in practice, then you can also model better what you can reallocate from one sector and what you cannot reallocate from one sector to another sector. So I think, although it's more difficult, you get a bit more realism quickly there. So I agree. So this paper should be seen as well, it's not applied theory, but it's trying to uncover some mechanism which should be treated in more detail later. The option value thing is another important one. So just say, looking at the transition risk, just when these guys are needing a lot of money to invest in becoming green, maybe invest in hydrogen factories, their borrowing constraints get hit. So they can't borrow the money to finance the green transition. So that's again something that needs to go in there. But so Ken, I think your point is very valid. Thank you very much.
Yeah, I think Rick has answered my point, but I was also thinking, as a micro-theorist, I was also thinking about the consumer optimization problem here, right? So these things like temperature are not only affecting the returns from these two sectors, but also affecting, if there's a terminal period that I'm optimizing with, it's affecting how hard that terminal period is. It's affecting over time the discount rate that I'll be using, my time preference. And all of those will work in favor of the green sector, in addition to what you have shown. And so obviously you can't have all of that in the model, but I just wanted to point that out, that you could do the same you can do a problem for the consumer, and you might get similar results.
So I think on the consumer side, so if you move away from the stochastics, so what I think is very important, both on the consumer and the production side, there are multiple equilibrium. So you may have strategic complementarities in utility. So maybe if a lot of people become green and then they change their preferences, maybe other people become green. And then we can very easily get a high emissions and a low emissions equilibrium. Similarly, on the production side, the cost for me of producing something like a solar panel will fall if lots of other people are producing solar panels. So something like Wright's law or Swanson's law, and so there are kind of technological spillover effects, and they're like also social spillover effects, and these typically can lead to high emission, to bad equilibrium and good equilibrium, and then you may not want to have marginal policies around the bad equilibrium, but you might want to have something more radical to shift, to have a big push to get it to switch the whole economy to the good equilibrium. That's one point. So that's one reason why looking at utility functions are important. And other reasons are behavioral effects. So we know that carbon pricing, from a psychology point of view, it's a bit like the weather. So in England, it's cold sometimes. So they say the temperature is 5, but the skin temperature is -10. It's very cold. So it's the same thing with carbon taxes. They may be only $50 per ton, but maybe people feel like it's 200. And this thing called salience is a big issue in behavioral economics. Indeed, Emmanuel Fari, before he died, published a paper with Gabin in the Journal of Political Economy exactly on these topics. And they really, that means that Thaler and people like that would suggest you have to optimize, find your climate policy, taking account of these psychological aberrations. So if you ask me honestly, because you asked it, I think these psychological effects are important, and these social interaction and these technological interaction effects are important. So what I've looked at is climatic tipping points or damage tipping points, but what are also important are, to get the whole thing going, are social tipping points, technological tipping points, political tipping points, and even institutional tipping points. So that if there's more of these things happening, then other countries will follow, other people will follow, and other firms will follow. And that's something which we as economists have not been so good at, but I think maybe in practical terms may be extremely important.
Thank you.
Okay,
Yeah, thank you.
Great. Simon?
Sorry, somehow I don't have that icon of hands. It's probably because I'm the host, so I have to raise my real hand. Thanks, Rick, for the great presentation. And then I don't think I have a question, but it's more like a query for clarification. So I began thinking about, in your model, this dichotomy of green versus the dirty capital. So how do we actually define dirty capital and green capital? And I try to relate that in the reality, in the real world. And so if we put in the money in the dirty capital, is that just about those production activities that actually cause the damage to the climate? Or it can be, for example, is it a company like produce pollution, but they might actually put in some investment to adopt some technology or equipment try to reduce the pollution. In that scenario, how we categorize that kind of capital? Do you call it green or brown?
So the way people are doing it at the moment, so not only we, but also central banks, for example, that you look at how much emissions are produced, maybe even at the firm level. So you say like a steel factory is obviously uses enormous amount of energy, fossil fuel coal, and that clearly is a carbon-based sector and a carbon-based industry. Same thing for aluminium, but then of course they could become, in the long run, they could become green, because if they were to invest in hydrogen, it's every schoolboy can do it, but it's not ready yet at an industrial scale yet. Because you need, there's maybe blue hydrogen, but to make hydrogen from, say, wind or solar energy, and then to convert into hydrogen and then bring it to the steel factory, we're not there yet. Maybe another 15 years or so. But for the time being, that's clearly brown. And then there are so typically people look, and then the power industries, if they're not on solar or wind, then they are brown. But of course, these definitions can change, because some companies or industries may flip from becoming brown to green, and then you need to look that into your data. But the way people do it typically is to measure the emissions.
Okay.
per unit, and I think even sometimes just emissions per unit of value added. So you see these classifications being done, and people are now trying to get international agreement on these things and things like that. And of course, when the IPC does it together with the OECD, it becomes quite political, because some countries think this is unfair and things like that. So there's a bit of politics involved there as well.
Yeah, and also I understand in your model you don't really allow the technology to change.
Okay, that's again for simplicity. Normally, what I do is, it's not important for the results we get here qualitatively, so we switch it off. But normally you would get, actually you would get an extra state variable, so it becomes a bit much more complicated to solve. But you would allow the cost to depend on the total cumulative use of solar panels, for example, of renewable energy. So we know that for every doubling of solar panels installed, the cost of one solar panel drops by about 30%. That's one, so that's learning by doing. And the same thing is true for batteries. The same thing is true for windmills. So if you allow for that these cost reductions in the future are not internalized by the market. So just like there's something called the social benefit of learning, that's showing that that's all the present discounted value of all future cost reductions resulting from installing one solar panel today. That's called the social benefit of learning, and that's a subsidy you should give for that. So then technology becomes endogenous. What we do and what we can do easily is, of course, and what we do a lot, what we normally, I think we've done it here as well, is to allow for exogenous technological progress. It's just a time trend, but it doesn't affect the policies very much.
Right.
And then the third way of doing, it, which I've not done that much, but it is, you can do as well, instead of learning by doing, is to have directed technical change. So you think of the models of Dado and Acemoglu, and then basically you shift. You have a fixed number of laboratory people, in white coats, and you can shift them for working for dirty laboratories to green laboratories, and try them to kind of do technological progress in a green direction. And then of course you have to subsidize that as well. So these are the three ways of doing. So you do it either exogenous, via learning by doing, or via directed technical change.
Right. Okay. Thank you.
Good.
Okay.
Good.
Ken.
Yeah, just related to Simon's point about firms having a mix of technology, I should point out, you probably know about this, Rick, that Perth's own iron ore billionaire, Andrew Forrest of FMG fame, he is pouring billions into establishing this green energy firm, so that the profits that he's making from iron ore, so very substantial profits, a lot of that is going into produce or setting up, trying to produce green energy, for green steel and the like, and he's flying around the world signing up agreements with any government that'll listen to him, apparently. That's Twiggy Forrest,
Right.
His own billionaire.
Yeah. So in a sense, this is echoed in other parts of the world as well, of course, because in the sense the Gulf countries are doing the same. They're trying to put a lot of their money into the new green industries. So in a sense, industry and even the fossil fuel industries and those billionaires you're talking about, they're much further ahead than maybe governments are, because they know where the money is going to be in the future. Yeah, so I think it's an extremely good point.
Yeah, great.
Good.
So yeah, so Rick, can I just ask two questions? One about theoretical, another is just empirical. So can you just still stay with us for a few more minutes, if you have a?
Yeah, I have a few more minutes, and then I have to go to a session. Yeah.
Okay. Yeah. So the thing is, I think it's very fascinating for you to share this two-sector model. It's just like a closed economy or global economy. But in terms of diversification, I'm also thinking about the diversification across regions, because this, for example, the temperature shock could be also quite heterogeneous around the surface of the globe. And then I don't know whether it is also promising for you to think about this regional specific model. You have many regions, so you can also allow you to diversify the risk across, not only across sectors, even within sector, you can also diversify across regions. I don't know whether it is promising. There's just an idea in my mind. Yeah.
So there's now people beginning to work on this. This Esteban in Princeton, Rossi Esteban, you know.
Yeah.
And then there's Tony Smith in Yale, and they look at a cell by cell level. They split the whole world into cell by cells. I think maybe 100 by 100 kilometers, maybe even smaller. And then they use satellite data. And then they get satellite data on the locals. Because a lot of stuff is micro temperature, so it can vary maybe 10 kilometers across. So you need a very fine resolution. So a lot of, and people, there's a big thing called the Climate Impact Lab, run by Solomon Ishyang. And they're doing a lot of that stuff on that level. So there's not so much stochastics, but then we finally can ask those diversification questions that'll be, I think, in 4 or 5 years from now, because people are beginning to develop these very detailed disaggregated models. The World Bank is doing it as well. So the World Bank now is getting data. It's a project I'm working with them on, but they're doing a lot of the heavy lifting. So they can see exactly in which factory from satellite data, all the emissions are coming. They can really account for it on a very, and the industry loves it. So Ben Caldecott is a guy in Oxford. He has this big network of industrialists, and they all want to know where the emissions are coming from, whether their factory is doing it or not, because they're worried about the risk of stranded assets. So, but of course, those data will also allow you to ask questions like diversification. So of course, we see that some of these shocks, if a port is destroyed by a flood, and typically costs are only maybe 1-2 years, but the trade diverts to a nearby port, and then once the port is recovered, it goes back again. So, but again, for that you need, and then there's migration. So maybe migration can also, there's a lot of adaptation stuff. So it's not only diversification, there's also adaptation, and the two are linked up together. So I think that's basically, people are just only beginning to think about it as we speak at the moment. So it's a great area for PhD students. That's what I think.
Yeah, thanks, Rick. Yes, my second question is about the empirical evidence you said about the differential risk rate on this brown sector and the green sector. You said, okay, the interest rate is usually higher for the brown sector, but I think empirically how to isolate or disentangle this difference to different factors. I think one factor, of course, is just the climate risk you talked about today, but I think in reality, there was some policy difference. The government really just, and also the banking sector, they really encourage the green finance. They give up some preferential treatment to these green technology, green sectors. So do you have any idea to disentangle all these different factors which contribute to the difference we observe in the tax rate, the interest rate difference?
No, not really. I have some, but that's what I'm interested. So we're looking into that and trying to understand it better. But I haven't got a clear answer on that yet. But I see but of course it's extremely important because people ask us this all the time. But there's a kind of missing link between academia and the real world.
My question just because I want to think. I'm thinking about how to empirically test some propositions or conclusions of your model.
There's a young guy who just a student of Lars Hansen, and he just started Arizona. He's called Michael Barnett, and he's doing some stuff on this empirically and finding some effects. So he's the only one I know. It's in his PhD, and I think it's also coming out in a review of financial studies.
Yeah, great.
But that's the only one. So there's not a collection of papers where to draw upon. It's really ongoing research, and the banks are all shifting into this area as well.
Yeah. Thank you so much, Rick. I think
thank you very much.
A very fantastic afternoon, and for your knowledge, in this
Thank you
field.
very
And
much.
I think your talk give us to show us the frontier, like where the frontier is and the direction that the PhD students and including us to do research in this field if we want. Yeah,
you're too kind. I look at your beautiful backgrounds. Ken's, Mark, and Simon with the Italian type thing. Would have been nice to be there. Anyway, thank you very, very much.
Hopefully, yeah. So we'll be more integrated, after the COVID.
All right, thank you so much, Rick.
Okay, thank you.
Okay.
Bye-bye.
Yeah, thank you.
Bye-bye.
Yeah, thank you. Bye.
Bye-bye.
Have a good day in
Bye.
Ploeg.
Thank you. Bye.
Yeah, bye-bye. Yeah.